Just wait a couple of minutes. We're a little early still. Some people like coming to class like sort of just right at like 1:30, which I respect. That's efficient use of time. I mean, if you're here like 2 minutes early, 2 minutes you'll never get back. Think about that. So I think today's lecture is going to be about 20 minutes shorter than usual. So some professors on election day don't have class, so that the people that are going to vote have time to vote. I didn't want to do that, but what I sometimes do is I decrease the lecture time by the amount of time it took me to vote in the morning. So this morning was much longer than usual. It was like 20 minutes. And that was fine, but they had like a bake sale. So while I was standing in line, you know, not only am I like, well, who am I going to vote for, but it's also like, homemade sticky buns, Dunkin' Donuts, chocolate chip muffins. There's a lot of decision making this morning. So the other thing I'm not doing today, which I usually do, is a quiz. So there's no quiz today, and again, it's election day. You guys might want a little bit of extra time. So for you guys that haven't been in the US for an election day before, you know, it's kind of a party time. People tend to like hang out together in the evenings and watch the results and stuff. It's really kind of like a second Halloween. There are parties and people tell scary stories, you know, try and frighten each other. And it comes around 4 years, so it's kind of like the Olympics, except we usually don't have to worry about losing to the Chinese. That's usually not the issue. So there's no quiz today, but you guys should probably sit down and review these slides. Sometimes when you have, you know, like if you're standing in line or something, I don't know. Okay, so let me go ahead and start. I'm going to take a couple of minutes to recap last week's lecture, just to kind of swap it in, and also because we're going to be using, you know, all these randomized algorithms use sort of the same kinds of ideas. So let's go back to Bloom filters. So you might remember these. So the basic idea is it's something like a set. You can add things to it, and you can ask if you've added something in the past. All right, but nothing actually gets stored in the Bloom filter. It's just like sort of, you know, setting a few bits kind of behind the scenes. So it's a very compact storage. It's also very fast, and what you lose is you lose the ability to say enumerate all the things that are in the set, and you also get kind of noisy answers. So if you ask whether the filter contains the string, then you'll get back yes or no, and if you get back yes, then you might have added the string in the past. Or you might have had sort of an unlikely series of hash collisions. If you get back no, then it's definitely not in the set. Okay. So there's some probability of getting a false positive, and you know that's something that you kind of like tune by setting the internal parameters. So the way the Bloom filter works, and this again, the same idea sort of happens in a lot of these randomized algorithms, is something like this. So when we add something, what we have is we're just maintaining this compact data structure. So it's just a one-dimensional array of bits, 0 or 1, okay? And when we see a new item, we use a bunch of hash functions to get a bunch of random indices into this array, and then we set some of those random bits. They're not really random, because they'll be the same every time we see that same string, because we'll get the same hash result. But you know, for the purpose of analysis, they're just sort of setting random bits in the string. So maybe we'll set these 3, and then we get another string, we set a few other ones, and there can be collisions, right? Because, you know, it's just setting bits in a string, it's just using a hash function. Of course, there can be collisions with a hash. So here I've got the blue things in blue, and this one here that's purple was a collision. So they're set by both of these things. But we can still tell what's in there to some extent. So if I ask whether Fred Flintstone is in there, what we do is we take those same random bits that we set, right? We apply the same hash function. We figure out what those 3 indices were, And then we look at them, and basically we return the min, okay? So if they're all 1, we'll say yes. If any of them are 0, we'll say no. Okay, so here we'd say yes. If we ask about Barney Rubble, of course we'd say yes. And if in fact we have added that string, then we're guaranteed to have set all the bits that are associated with it. So we'll always say yes if it's in there, okay? And usually if we ask about something that's not in there, we'll say no, right? Usually if we ask about something that hasn't been added yet, we'll generate a bunch of hash functions, and some of them will be for indices that haven't been used yet by anybody else, okay? In which case we'll see, oh, well, one of those is not set, so it hasn't been added yet, so we'll say no. But sometimes we'll be unlucky and we get a whole bunch of collisions, right? So here we've collided twice with these blue things and once with this red thing. So in this case, we would say yes, even though we didn't put Wilma in there, so that's a false positive. So this is kind of the price we pay for the Bloom filter. And the implementation is very simple. You just allocate a bunch of bits. You pick a bunch of hash functions, okay? And then every time you have a string, you set the appropriate bits in that array, 1 for every hash function. And again, when you're checking, you just see what, say true if they're all set, otherwise false. And then the only kind of math in there is figuring out how to set the size of the hash table, the array of bits you're hashing into, and the number of hash functions, right? And their formula basically for setting these, if you know how many things you're going to add, and you can sort of dial in a probability of a false positive, and the Bloom filters are very robust. They will have that behavior. So that was the first data structure we talked about. Everyone remember that now? Nod your head if you want me to move on. Oh, okay. Nobody's nodding their head. Oh, I'll move on anyway. I don't care. So the other one we talked about was the count min sketch, which is actually kind of similar. So instead of an array of bits, we have a matrix of real numbers. So it's a D by W matrix. We pick a bunch of hash functions, ones before. And now what we're storing is not just an element, but we're associating an element with a real number, okay? So we get some string S, that's the key, and some value, okay? So C is a number that we want to increment the associated value of S by, right? So this is for keeping a running count of the number of times something happens, okay? So maybe this is like, think about this as, it's like we've got a bunch of names and we record the number of times they, I don't know, won a Kaggle competition, okay? So every time someone won a Kaggle competition, we put their string in there and we put like a +1 because they've had one more competition, okay? And to retrieve the value, you basically do something a lot like the Bloom filter. So we're hashing, and the math for the min count sketch, the count min sketch suggests you keep the buckets for each hash function, separate. So that's why if you have D hash functions, you'll have D rows. So you hash into the row associated with that particular hash function. And then when you retrieve a value, you take the min of those, all right? So the picture looks kind of like this. We've got here 4 hash functions and a bunch of columns here. We've got a string and we've got something where We talked about one application, which was finding counts for frequently co-occurring words for semantic orientation. In my experience, the Countman sketch is a really useful data structure, but it's somewhat harder to tune than a Bloom filter. So the bounds that you get on its performance are tight, and they're very sensitive to properties of the data. So often you're using data where there are a few big numbers and a lot of smaller numbers, so there's some sort of skew, but you don't really know exactly how much skew there is, or you may not be able to sort of parameterize how much skew there is. So you can sometimes have a much smaller filter than the kind of naive bounds would suggest. So basically, the size of the Countman sketch turns out to be a hyperparameter you got to kind of play around with. So that's a sort of a disadvantage of the Countman sketch. Still a very useful data structure for a lot of purposes. All right. So now we're going to move on and talk about locality-sensitive hashing. And if you've been basically, for the last few minutes kind of like this, it's like, okay, he's just reviewing. I saw this last week. It's not important. This is when you should wake up. Okay, we're covering something new. Okay, locality-sensitive hashing. This is not something I've talked about before. Okay. All right. So everyone's awake. Okay. So here's the idea. It's a different data structure. Okay. So a Bloom filter is kind of like a hash set. Okay. The Countman sketch, it's kind of like a hash table where you're associating some object with a real number. Okay. So in locality-sensitive hashing, the idea is for every object, what I'm going to do is I'm going to construct a very compact, concise representation of that object. And these representations are going to preserve similarity. Okay? So my object is going to be a feature vector. Okay? So any sets of features I want can be in really large dimensional space if you like. So it could be, say, a document. And we're going to turn it into a bit vector. And this bit vector is going to be, maybe 32 bits long, maybe 256 or 1024 bits long. There's going to be basically just a handful of words of computer memory, right? And the idea is that similarity in this bit vector space is going to preserve similarity in the original vector space. Okay? Question?
Similarity would be what?
Similarity. Okay, good question. We'll get to it. So what do I mean by similarity? So the cosine similarity between two vectors will be closely related to the Hamming distance between two bit vectors. Okay, so Hamming distance is the number of bits they disagree on, and cosine distance, the angle between two vectors. Okay. So that's the similarity that you'll be able to preserve, but the main point is you can do similarities between these bits very easily, and they don't take up much space. All right. So what's the trick? So we haven't talked about anything here that really sort of talks about similarity. We've kind of talked about collisions, right? And sort of the key idea in the randomized algorithms is you use multiple hashes to control your probability of collisions, all right? So for locality-sensitive hashing, we use another kind of key idea in randomized algorithms. And this is an idea which also comes up all the time. Okay, so again, wake up. So the idea is a random projection. All right, so this is one picture of a random projection. So what we have here is we have a three-dimensional structure, the Earth, okay, and I projected it onto 2 dimensions, the dimensions of that projector screen, okay. So this is a 2-dimensional projection of a 3-dimensional object, okay, and you can see most of the things that would be close together are still close together, okay? So here we've got, Melbourne and Sydney, and they're close together. Here we've got, I don't know, that's Philadelphia, that's Pittsburgh, and this is DC, right? Okay, they're pretty close together, all right? But there are also some kind of false positives. So here Costa Rica seems to be pretty close to, I don't know, that's somewhere in Indonesia, right? I don't know where that is. But it's not, in real life, close to Costa Rica, right? We've got Sri Lanka here is very close to Cuba, okay? Again, not the case in reality, okay? So some of the distances are preserved, and then some of them are screwed up, okay? But the key idea is if I did this randomly, so let's imagine I took this globe and I just spun it around. I just had it in my hands, I could bounce it on the ground and hold it up again and do another projection. I would get a similar set of things which are where a similarity is preserved. Most of the things the similarity would be preserved, right? It would just be distorted a little bit for things that are kind of like, on the side of the globe, right? So most things, the similarity would be preserved, and we get a different set of false positive similarities. So if we aggregate over a bunch of these different projections, maybe we can get a good estimate of similarity. So that's kind of the intuition. Let's get a little bit more mathematical now. All right, so here's the picture we've seen before. We've got a bunch of points. These happen to be separated by a hyperplane. But let's just pick two of these points and ask, so a hyperplane would basically be, a projection in this case is a hyperplane, okay? It's any line that kind of goes through the origin, all right? So if I pick two random points and ask whether the projection preserves similarity, they're basically two choices, right? So one is they happen to be projected onto kind of different places, so that's okay. These are in fact kind of distant points, right? So you'd expect they should be projected to different places. And that's not necessarily the case, right? I can make these points as close as I want because I can pick some line that actually is orthogonal to the line between them, right? So they're connected by some line. I can pick something at right angles, and then when we project, they'll be really close, okay? So if I choose the wrong hyperplane, they will be close. But if I just choose a random hyperplane going through the origin, they probably won't be, okay? So if I choose some other direction, like this one, and then project onto it, those points are still distant, okay? So this is the key idea. So if I take a random linear classifier, basically, all right, and I score 2 points with that random linear classifier, if they get the same score, they're probably close. They were probably close to start with, all right? So this is the idea of a random projection. So random projections usually preserve similarity, so we can use this to make a hash code. So here's the basic idea. What I'm going to do is I'll repeat several times. I'll pick a random hyperplane, okay? And how do I do that? Well, I'll just pick random weights for every feature. So if these things I'm classifying are documents, maybe they're documents over a vocabulary of 10,000 words, I just pick 10,000 numbers, say from a Gaussian, okay? And then I score things. I take a look at the inner product, and then I basically look to see whether the inner product between R and X is positive or not. Okay, if it's positive, I'll put a 1 in the next bit. If it's negative, or 0, I'll put a 0 in the next bit. Okay, so I'm basically taking these random classifiers and I'm representing something as a bit vector where each bit indicates the score, aggregates the score. So the score is positive or negative with respect to that random classifier. Okay, so the theory says that if you have 2 points that have small cosine distance, then the bit vector encodings will have a small Hamming distance. So that's the idea, all right? So let me show you this idea one more time. So here's a point, okay, and I'm going to encode that point. So I start off, I come up with a random hyperplane, which is a random point here, and then I figure out whether it classifies this thing as positive or negative. All right, let's say it's positive here. Okay, so this is the direction we're looking at. Okay, so the first bit would be a 1, so I've got this. Then I pick another random hyperplane, and it's a negative, so I'll put a 0 there. Okay, and then I pick a whole bunch more hyperplanes, and some of them are positive and some of them are negative. And this is kind of what you'd sort of expect to see, right? What we'd expect to see is we'd expect to see a lot of things at different positions, right? And the particular bit vector is basically saying which slice, in this pie, which slice of pie this particular point is in, okay? And of course, in cosine similarity, what we really care about is the angle between two things. So if something is in exactly the same slice of the pie, right, then it's going to have exactly the same bit vector. And if something is nearby, it'll probably have a similar bit vector. So for example, if I take this yellow point right here, it's going to agree on every point except for this one right here, okay? This one calls this guy positive and this guy negative. So there's one case where they disagree. All right, so for these 2 points, the pink point and the yellow point, the Hamming distance should be 1. So there's 1 bit they disagree in. The signature length is 6, so there are 6 bits. This bit encoding is sometimes called a signature. So the result, the formal result is the cosine of the angle between those 2 vectors should be about the cosine of this quantity, okay? The Hamming distance divided by the signature length. So here that's 1/6. So that's an estimate of the cosine distance. All right, so that's the key idea. So just to give an idea of how you might use this, here are a couple of examples. So here we've taken a bunch of, I'll get to the details in a second, but think of these as documents for now. We've computed their actual cosine distance, all right? So that's the x-axis right here. And we've computed their approximate cosine distance based on this Hamming distance score. So here we've got 32-bit signatures. So of course, there are only 32 different Hamming distances, so everything is kind of in these bands, right? So that's the approximate distance, right? This would be the line y equals x, all right? So you can see, there's certainly some correlation. It's not great, all right? But if we get to, say, 256 bits, we're starting to see a pretty good correlation. And interestingly, the correlation's not that high for things that are quite distant, right? So if I fix 2 points that are like very different, across, these all these planes, then we see sort of a pretty wide spread in the approximate cosine scores. But often we don't really care about those things. Often the reason we're looking for similarity is we want to do something like, say, k-nearest neighbor or clustering, when most of our decisions are driven by the things that are highly similar, right? So the things that are highly similar and how well they correlate is really much more important. So the fact that this spreads out down here, it's like, well, that's not great, but what we really care about is how well things correlate for the very highly similar things. And here, they really are quite well correlated. All right. So I told you what you do with Bloom filters. I gave you some ideas what you might do with a count and sketch. So here are some things you might do with locality-sensitive hashing in general. Okay, we can store the data and still compute similarities really quickly, and we can store it very compactly. Okay, so one thing that's nice about locality-sensitive hashing, it gives you a really fast kind of approximate nearest neighbor method. You can just look at all the things that ended up with exactly the same signature, Hamming distance 0. Those are the things that are most similar. If you're just doing k-nearest neighbor, that's kind of a good cut. Maybe you take those things first and do some additional similarity computation on those. There also, it turns out there's some pretty fast nearest neighbor methods that are for bit vectors with the similarity metric of Hamming distance, right? So there are some kind of like fancy tricks where you sort on different bits and aggregate those sort of distances. So there are tricks that give you pretty fast nearest neighbor computation in this Hamming distance space. And of course, you can also do a very fast approximate clustering. You can just take a bunch of things that have the same signature, and those are likely to be very similar. So there are a bunch of things that you can do with this. This is kind of the general story. What I'm going to do next is I'm going to talk about a kind of particular application and also some tricks that make this technique more powerful and more practical. So first, are there questions about what I've got said so far? Any questions about American politics or where you're voting? No, okay, never mind. Okay. Okay, so this is a paper. Ben Van Derme, I was on his thesis committee. He's at Hopkins now. And Ashwin Lal, who I don't know. So they were looking at use of locality sensitive hash functions. This is the algorithm, okay? I haven't really told you the algorithm yet, but here's the algorithm. So first what I do is for each bit in the signature, I'm going to draw a random weight for that feature. Okay, so I'm going to draw something from a normal distribution. And then for every instance, I'm basically going to compute the dot product. Okay, so I'm going to sum all the values of that instance feature times the random weight for that feature. Okay, I only have to do that obviously for the things that have non-zero weight in x. Okay, and if that's more than 0, then I'll return 1. Otherwise, I'll return 0, and that's the bit. Okay, so this is the bit vector. Okay, it's not a complicated algorithm. All right. Now there's some disadvantages with this. Okay, so here's one disadvantage. So supposing I have 100,000 documents. So those are my my x's. All right, and I store them with these 256-bit signatures. Okay. So the documents were really long and big, and they got lots of words in them and stuff like that. And now 256 bits, okay, that's 32 times 8. Okay, so it's just 8 words of memory, very compact. Okay, but there is a downside. Okay, so the downside is I also need to store these random classifiers. Okay. So I've got 256 random classifiers, and each one of them has a weight for all the 10,000 words in the vocabulary. So yeah, my data is stored very compactly. But if I ever want to update that data and add new things, for example, then I got to go back to this gigantic database that's got 256 dense classifiers, right? So that's an expensive thing, all right? So one problem with the naive algorithm is that storing all those classifiers is expensive in high dimensions. Okay, I mean high dimensions being like large vocabulary. Okay, so we can get around that, right? So we could basically just store the random number seeds, right, and have a pseudo random generator here, so we always get exactly the same classifiers. I just store the seeds. Okay, that's totally reasonable. That's a little fragile, okay? And you also kind of have the disadvantage that I can't, I could completely reconstruct all those random classifiers from scratch, but if I just wanted to, poke at them and say, well, what's feature value, what weight does this classifier have for this feature value, I can't do that without reconstructing all of them, all right? So we could do it, somehow by storing seeds and reconstructing things, but it's a little bit fragile. So here's another idea. So this is a really neat kind of practical trick. It works for a lot of different things, and it's called pooling. And this is due to Van Derme, who's done a lot of work in this area. So here's a different algorithm. All right. So the bottom part is the same. Okay. Basically, we're going to just do an inner product-y kind of thing. All right. But instead of drawing a different random number, a different weight for every feature for every classifier, what I'm going to do is I'm going to do those random draws in 2 stages. So first I'm going to construct something called a pool. So a pool is just going to be a set of random draws. Okay. So my pool is just an array with, I don't know, let's say 1,000 things in it, or maybe 10,000 things in it. And I'm just going to draw one random number and stick it in that pool. That pool is going to get saved, okay? So the pool is something I keep around, but it's only 1,000 numbers. It's not a big deal, okay? So now to get a random hash function, okay, what I'm basically going to do is I'm going to look up an appropriate index in that pool, okay, right? So each one of the features that we have is, let's say, also a string. So maybe it's a word in the vocabulary. So So I can get the value of the ith hash function on that feature. All right, so that corresponds to a particular weight from the classifier, weight in the classifier, and that classifier is somewhere in the pool. Okay, it's some random number I would redraw from the pool. So rather than draw something randomly, I'll just use that hash function. So I've got a hash function on the features that tells me what random weight to use, and that random weight is basically the pool. Okay, and index into the pool. All right, so we pick up that weight from the pool, and then we multiply it by the value of x. So this is now my new inner product. All right, so before what I do is I would take the weight in the ith random classifier, okay, associated with feature f. All right, now I'm doing this kind of subtler thing. I'm taking a hash function, the ith hash function for the feature f, okay, which is I'm interpreting as a random weight by saying, well, it's a random weight drawn from this pool, so it's a random position in this pool, okay? And I basically do the inner product, between the original vector and those transformations of it, okay? And then, once again, we threshold it, that's the next bit, and so on and so forth, okay? So this is the idea. So now I don't have to store all the classifiers, I just have to store the pool. This is basically the way of getting any weight for any classifier, any random classifier, okay, just kind of on the fly. So it's very transparent how these things are constructed, all right? And the only problem with this algorithm is that, technically it's wrong, right? All the math is for randomly drawn classifiers, right? And these aren't random, there's some sort of weird correlation because they're sharing these random values from the pool. So when I said, put 1,000 numbers in the pool, it's like, well, actually, that's not really so good, right? So this is the error between the pooled version of the, I think this is actually looking at the error of the inner product. This is an error looking at the difference between the pooled version and the non-pooled version. Okay, so with 1,000 numbers, it's really not so good. If you get to 10,000 numbers or 100,000 numbers, there's really a pretty small error. Okay, so this technique does, in fact, in practice, save a lot of space at the cost of introducing sort of a very small kind of additional error. And of course, errors are going to be accumulating further down this process. So we can probably afford to introduce a little bit of error here. Okay, so this makes LSH a lot more practical. Okay, so this not only is a compact encoding of the data, but it also gives you a compact encoding of all the classifiers. All right, so that's good. So Van Derme went on and did something else, which is kind of cool that I like talking about. So, so basically, they showed how to do this in an online setting. So this is the problem they were looking at. They were looking at something called distributional clustering. Okay, so this is another kind of standard NLP kind of task. It's closely related to these word-to-vec type embeddings for words. So basically, we want to come up with an interesting similarity metric on words, where words that sort of appear in the same context look similar. So the basic idea is for every word, you construct a vector, a sparse vector of all the words that co-occur with W in some specific large corpus. All right. So now for every W, you have a vector, and you cluster those. All right. So for example, here are some. Here's a word London. All right. Here's some random occurrences of London in text. Okay. Right. So if you want to find out what words co-occur with London, usually we look at a short window. So here we've got 4 words before and after. Okay. So every word in this window would basically be added to V. So V is basically a document of all the co-occurring words. So here, it would have things like Pentonville and prison and werewolf and remade and Monmouth and so on and so forth. Okay. So this gives us like a document representation of each word. And now we can look at similarity. And just to give you an example, if we look at what London is similar to, right? This is using the gigaword corpus, so a pretty big newswire corpus. So cosine similarity of 0.95 or better for Milan, Madrid, Stockholm, Manila, Moscow. Okay, it kind of seems reasonable. And some other words like sold is kind of like deployed and presented and sacrificed, you know, at least sort of similar part of speech things. All right, so this is the idea. I think I have time for an anecdote. Okay, so at a conference this summer, I ended up like chatting with this guy that had been in this course a couple of years ago, he worked for Snapchat. Okay, I remember it was Snapchat. He was like sort of doing selfies and trying to switch our faces and stuff like that. But he worked for Snapchat, which is a good place to work. And he said that when he was interviewing, I don't remember if it was Snapchat or not, but when he was interviewing, one of the potential employers basically asked a question about exactly this algorithm. So I was kind of afraid to ask the obvious follow-up question, which was, did you get it right? But yeah, I gave him a chance anyway. So anyway, this is a cool algorithm. Maybe someday you'll want to know about this. Maybe even before you're interviewing. I don't know. It could be like exams or something. I don't know. Anyway, so here's the Van Derme trick. So here what we're trying to do is we're trying to do this online. Okay. So what I want to do is I want to scan through this big corpus. All right. And at the end of it, I want to have the LSH signatures for every word in the corpus, okay, with respect to their context. And all I want to do is just scan through the corpus once to do that, okay? Sounds hard, right? I mean, really, we should like sort of go through and collect these document vectors and, you know, do some transformation and so on. But here's the basic idea, okay? So notation, so V is going to be the context vector, so that's what we're transforming a word into, okay, all the co-occurring words. RI is the ith random projection, okay? And this is basically the ith bit of the signature, right? So this will be 1 if the inner product is more than 0 otherwise, okay? So that's just 1 bit of the LSH encoding. So here's the key idea. So it turns out this vector, which is summarizes all the co-occurrences of word W in the corpus, okay? It's actually the sum of a whole bunch of smaller vectors, right? So every individual mention has a bunch of words that co-occur, and those all get summed up to create the eventual vector V. So this vector V down here, right, the way it's produced is you go through and you get this one and then you get this one, right? And we could just basically say, well, I'm going to aggregate everything and construct a vector at the end. Or I could start here and say, well, there's a vector for that sparse vector for that word co-occurrence, then a sparse vector for this word of co-occurrence, and a sparse vector for this one, and then I'll sum them all up to get the final vector. Okay? So we could take this vector and write it this way. Okay? So then we can do just a little bit of distribution. So this inner product with the random classifier, okay, it's also the sum over all the mentions of that mention representation, that mention context vector, times the random classifier. So that's just distributed. That's just using the distributive property. Okay. So what I want to do at the end of the day is get this bit. All right. I want to get each of those bits. Right. And I can do it using this little identity. Okay. So the basic idea here is replace this guy with this summation, right? And what we're going to do is we're going to scan through the corpus, and when I get to the teeth word, I'll look at that the context around that word. That's going to be some particular VJ. I'll dot product it with a random classifier, and then I'll keep a running score. So now, basically, for every bit that will be in the final signature, okay, I've got a running total, which is a numeric score. All right, so that's 30 times bigger than the final thing I'll come up with, but maybe I can still store that, you know, in kind of an online setting. So this is the key idea: is we're going to take one of these contexts at a time, right? And we'll keep a running score of these inner product things, which are all additive. All right. So we're storing not a bit vector, but a running tally for each bit of each word. So that's the end of it. That's basically the whole idea behind this online streaming paper. That and the pooling. So when you combine these things together, you get something like this, okay? So first we construct our pool, okay? Then I'm going to get a hash table that maps words to floating point arrays, okay? And there's one array for each dimension. So this is basically our kind of big intermediate approximation of the dot product that we're keeping, all right? We initialize the pool, all right? And then I'm going to go through the corpus in order. Okay, so with each word, I collect all the context words. So that's a bunch of features, okay? So in Van Derme's representation, I think these are binary features, okay? So you're either adding RI or not, okay? So RI is basically this quantity here, right? So this quantity here is the jth hash of that feature, okay? And S is just sort of a random seed we're using for that. Okay, so this is the hash of the feature, all right? And then if I take that and index into the pool, that gives me the weight of that feature in the ith random classifier, okay? Because I'm using the ith, I'm sorry, yeah, the jth random classifier, right? Because I'm using the jth hash function, okay? All right, so this is, and then the feature is either 0 or 1. I'm looking at the non-zero features. They all have value 1, right? It's just binary features. So I don't have to multiply by the feature's value in, the value of fi in that context vector. I just add it in, okay? So this step right here is keeping this running tally. So we're updating h for that word and that dimension of the signature with that sum. Okay, and then finally, at the end of the day, I basically construct these signatures by thresholding those, right? So we go from a real number to 1 or 0. Okay, so that's the algorithm. It looks a little bit obscure, right? But it's basically sort of a combination of this fact that you can unroll things using this online version, and the fact that you can use this pooling trick to sort of very succinctly represent all the weights of these random classifiers. All right, so here's an experiment, okay? So they took 700 million tokens, so moderately sized corpus, and they looked at a representation of all the bigrams. So they've got 1 million bigrams, okay, and we want to look at similarities of those. So we were going to build a signature for each of those 1 million bigrams. If I'm using, let's say, 128-bit signature, then I have 128 million floating point numbers that I'm keeping track of. That's the number of accumulators I'm keeping, okay, as I'm doing the online pass. And then it gets squished down to something much smaller. It gets squished down to something that's, basically, 1/32 the size in terms of bits. Okay, all right. So we're going to build a feature vector of words that co-occur it using this online algorithm, and then it's expensive to do this for a whole corpus, but it's not that bad to do it for like some selected set of words. So they looked at 50,000 bigrams, and they computed things the correct way. So here's some results. So this is using 2 to the 4, which is, I'm going to say 16, then 32, 64, 128, 256 bits. So this is the error that you see. So you can see as you get more bits, then you get smaller and smaller error. And here's some qualitative numbers, just to give you an idea how this kind of pans out. So here is London and the things that are closest according to the true cosine, all right? And these are the things which are closest in Hamming distance according to various measures. So, of course, there'll be many things that are tied, especially with smaller signatures. So they're it's randomly ordered kind of within that set. So for 16 bits, you get kind of, I would say, nothing really, right? There's maybe these 6 maybe a little bit more proper nouny, but that's all I get. With 32 bits already, sort of 3 out of these 4 things are cities. 3 out of these 5 things are cities. Okay. Now at 64 bits, they're all cities, although I'm not sure if they're ones that are kind of representatively close to London, right? 128 bits, 256 bits. I don't know which would be better or worse in a real application, but there's nothing sort of intrinsically wrong, with putting Stockholm before Milan, right? Or putting Taipei in there. Well, I guess it's not a European capital, but who knows, right? I mean, these are very reasonable approximations. So, any questions? Yeah.
So the Asian pool that you're selecting, how important is like sampling from normal, or why not choose something?
Well, so what you're sampling from is the same thing that you would be sampling the weights for the random classifier from. Okay, so a normal distribution is one choice. So there are other ways of constructing these random projections that work as well. So you can also, another kind of common choice is to choose something like plus or minus 1 or 0, right? So you choose 0, some fraction which tells you how sparse the random projection will be, and you choose plus 1 or minus 1 with some other probabilities. So if I remember correctly, the asymptotic math for those things is similar, but in practice, you need a few more bits to get the same sort of accuracy if you're using these kind of sparse, kind of 0, negative, plus 1, minus 1 weighted classifiers. There may be other things, other ways of constructing these random classifiers that I'm not familiar with. But the key idea is in the pool, they should be the values that you would associate with the feature weight in the random classifier. So they don't have to be normal. Okay, normal is one way of doing this math. So there are actually some advantages to making them, be, discrete values from a. So you might be able to simplify it like the online processing if you know all the weights are going to be plus 1 or minus 1, for example. So, yeah. And again, I guess I don't know what the consequences of, like, if all of the classifier weights are either plus 1, minus 1, or 0, what does the pool look like? How big does it have to be? I mean, obviously, it only needs 3 things in it. So, yeah, I'm not sure. That's a good question. Any other questions? Okay. But I guess the other thing is like the pool size. If you're storing weights or even signatures for a large number of objects, which is what you're doing in this case, having like an extra 100,000 parameters that represent the pool, sort of not a major problem. Okay. So like I said, I don't have a quiz today. There is a list of points you might want to review later. So I guess the things I've talked about is basically these 3 algorithms: Bloom filters, Countman sketch, and locality sensitive hashing. So Bloom filters basically give you a very compact way of representing a set with a little bit of noise. The Countman sketch basically gives you a very efficient way of storing counters, running counts, and they're accurate for the large counts and not necessarily accurate for the small ones. Okay, and LSH gives you sort of this fast approximate cosine distance and a compact storage that preserves distance. And they all, if you kind of think about these things, they're sort of really only a couple of ideas, right? So all these things, one of the key ideas is you're using hashing and multiple hashes to control the probability of a collision. So by having multiple hashes and changing the size of the space you're hashing into, you can sort of dial up or down the probability of collisions any way you like. So this is sort of like a key idea. And then there are a couple of other things that we talked about. So one was basically the pooling idea where you compress a lot of random draws by just having a pool. And the other one, which is again something which kind of comes up all the time in, all right, that's got to be some sort of sign. So another thing which comes up all the time in randomized algorithms is the use of random projection. So that, again, that's a very robust and useful technique for sort of pulling out some information and preserving similarity. Okay, so I said I was going to stop early today. I'm done. Okay, see you guys Thursday.